Okay, hi everybody, I am Fardin. I am part of the Michelangelo Deep Learning Platform team in Seattle. I spend half of my time working on Horovod, so just so that you guys know, Horovod team is actually in Seattle. Today I'll talk about basically what it does, some of the new stuff that it has, and how it can help you to do deep learning faster and easier. Just to start with some basic introduction, in deep learning, you have a bunch of layers. You have an input data that comes in and passes through these layers. And after a bunch of magic, you make some predictions. But to train these layers, usually the process is that you have a bunch of labels that come and are combined with the predictions that come out of your layers, go through a loss function, and then a bunch of gradients are computed, and then those gradients go backwards and are applied to your layers and update the weights of each one of these layers with gradient descent. And that's how gradually, with more data, you train your layers and you get better, whatever the metric is you're looking for in your loss function. Now, we usually have the problem of more data, which is a good problem to have. Like you have a lot of data and you want to throw it at your model. So you need to distribute this training. There are basically two common ways for distributed deep learning. First technique is basically model parallelism, where you shard your model into different components and you put each one of those components on a GPU on a machine. And then that machine or that component is, that host is in charge of training of that shard of the model. The second common way for distributed training of deep learning models is to have basically entire model live in one GPU, but then you shard your data. So it's called data parallelism. And we're going to talk about a little bit these two techniques, compare their pros and cons, and then talk about Horovod that uses a data parallelism basically model. So let's talk about data parallelism a little bit. What data parallelism does is you have identical basically training processes living in multiple GPUs or hosts, whatever you want to call it. You shard your data, so each one of hosts accesses a partition of the data. It does the regular model in aware of the existence of other processes, calculates the gradients. In step 3, basically, all these models have together to calculate the averages of the gradients that they calculated. So whatever technique they use, they calculate that average, and then at basically step 4, every model applies those averages to their local version, and that's this process keeps going on. So the difference here is that basically each process only works on a subset of the entire data, and that's what's called data parallelism. With the increasing amount of data, actually this is becoming a really good technique, sort of becoming the standard practice in many cases. The intuition behind it is that you have a lot more data, but that does not necessarily mean that your model's complexity has to grow. So models still fit in one single GPU, but you just want a technique to be able to shard your data and do this training faster. So new GPUs can like fit most of the models, and that's basically a good good thing that we have these days. You can also mix and match between model parallelism and data parallelism. So you can, inside one host, do basically data parallelism, but then, between different hosts, you can do data parallelism, but inside one host, you can do model parallelism. You can have multiple GPUs on one host that can do model parallel training. So, and that would be basically something like this. That you have each host, and each GPU in a host is in charge of a subset of the model parameters, but then across hosts, you're doing data parallelism. So they partition the data and each one train that. Now, there is the other the other common technique, and that is within data parallelism parameter service. So this is a technique that sort of is a standard if you use distributed training with TensorFlow or PyTorch. You're going to end up using most of the times use a parameter server. So parameter servers can be one of the ways that you can use data parallelism. The way they work is that you have separate workers that are, or servers that are in charge of keeping track of the parameters. And then you have GPU workers that are in charge of taking the data, calculating their gradients, and then sending that to the parameter server. And then parameter server takes these deltas and calculates the weights and sends them back to the workers. So there can be basically synchronous parameter server, synchronous SGD or asynchronous SGD that can be used in these in basically parameter server paradigm. The pros of parameter servers are that they are fault tolerant, especially if you use asynchronous SGD, because every worker is sort of independent from every other worker. But the cons are that the usability is usually a little bit harder because the model is more tightly coupled to the server. So you have to, if you have a larger model, for example, you have to shard the model, keep track of which parameter servers in charge of which range of models. And that can add to the complexity of your system to maintain and to basically work with. It also has a scalability issues because if you notice here, the parameter server is the bottleneck, right? If you add more workers, your parameter server is going to become the one that gets congested, and you have to just keep increasing that. Again, that becomes a complexity problem. And then you have the convergence problem if you use asynchronous SGD. So asynchronous SGD is basically the case where each one of the workers independently get a shard of some data, the latest weights from the parameter server calculates the deltas and send them back to the parameter server. But at the point where they apply it, the weights of the model on the parameter server might have been stale. So sort of that might do more harm than good, and it might cause basically worst convergence on the side of your weights of the model. So most people prefer these days to do synchronous SGD, but then that's like another story. Now, the other paradigm with data parallelism is what we're going to talk about in the next slides. But to introduce that, I'm going to first introduce an operation called all reduce, so that you understand what happens in the next paradigm. So all reduce this language comes from the HPC world, where they had supercomputers and all. And basically, all reduce operation, an example of a sum all reduce is that if you have 4 workers and each one of them has a set of values, if you do an all reduce operation, at the end of it, all of these workers have the sum of all the values that were present on all the workers. So you do all reduce operation, at the end, worker A has the values of all the values that were present on all the workers. So this is an sum all reduce operation. There is different ways of performing sum all reduce, but one that we use in Horovod is ring all reduce. There's also other techniques. There are many optimizations that happen down there. I'm not going to go into the details of this example, but it's basically the protocol of how the all reduce is actually implemented, which causes to have very good network bandwidth utilization, and etc. So now we know what all reduce is. So with all reduce, with having all reduce, the second way you can do a data parallel training for a distributed deep learning model is using this ring all reduce, where you have your workers individually working on a partition of data, calculating the deltas on the gradients, then doing an all reduce across each other. So they all do this, share these deltas with each other and calculate the average of the gradients across all the workers. And then applying that average into the weights on their own local version. So this is another way that you can do distributed deep learning. So this technique is bandwidth efficient because it uses network much more efficiently than other approaches. It's also much more scalable because you are doing a, sorry, it's not many to many, because there is no one single there's no one single node that is the bottleneck here, right? Everybody does more or less a similar job here. And it actually has a better convergence because you can use synchronous SGD. So what does synchronous SGD means? Everybody does one step of training, you average it, and then everybody applies that average gradients at the same time to their local version. The cons is that it's a little bit, it's not as fault tolerant, especially compared to asynchronous SGD. If one of the workers fail in this ring, then your training fails and you have to restart from the latest checkpoint or find another way. So this is what Horovod does actually. So Horovod is the library for distributed deep learning that was created here in Uber, Seattle, especially. It uses RReduce under the hood. It works with stock TensorFlow, Keras, PyTorch, and Apache MXNet, so no modification to those libraries. It only requires really 5 to 6 lines of code change in your existing single GPU script. So you don't have to do a ton of work to make it work with your existing scripts. It's a pip install Horovod to install it. I mean, you also need to install a few other packages, but like the core of it is actually a pip install Horovod. And it does a ton of optimizations under the hood to take advantage of your network capabilities. So RDMA, GPU Direct, ROC, etc. The paradigm that Horovod basically tries to serve is separating infrastructure from the machine learning engineer. So there's separate concerns here, right? The infra team provides the containers, the MPI environment for doing RReduce, allgather, etc. And then ML engineers only like they use exactly what framework they want: TensorFlow, Keras, PyTorch, MXNet, whatever they like. And then they sort of there's very good separation of concerns with Horovod. Horovod also has very good scalability. So this is just some benchmarks. Actually, they're kind of old, but you can see that even up to 512 GPUs, you get, so the top part here is what you would have gotten if you had individual workers multiplied by that. And like you're getting up to like 90% linear scalability with this many workers. So the performance keeps going on pretty steadily with the number of GPUs that we have. So that's another good thing that I think a lot of you guys would like, right? So now I want to show a little bit how we use Horovod. So like I'm going to show some code to just sort of make it like, to break the magic, right? It's not complicated. So to start talking about Horovod, I want to first introduce this concept of hosts and ranks. This again comes from the high performance computing, basically terminology. So basically in a Horovod job, like in this case, 2 hosts, and each host having 2 GPUs, there are in total four basically workers, right? Each GPU, each worker is assigned to 1 GPU, or each training process is assigned to 1 GPU. So you have a global rank, which in this case, you can see rank 0 to rank 4. But then within every host, there is also local ranks, right? Like rank 0 and rank 1. And then in Horovod, there are APIs to ask what is the size of the world, which would be 4. Or if every worker queries what's the local size, it is 2. So with this sort of understanding of what hosts and ranks are, this is a simple, very simple PyTorch script that it won't compile. So I mean, it's not that simple, but it's not that accurate. But more or less is a good representation of what you would need to add to your PyTorch code to make it work with Horovod. So I'm going to highlight one by one the lines that we have added compared to the standard PyTorch, and then later on we'll talk about why we have added each one of those lines. So basically, you have to import your library. It's a Python package, and then you have to initialize it, right? And this is pretty much standard always. You don't have to do, it's as simple as that, you can see. Second, you have to basically pin the GPU to this rank that's running this script right now. So you are querying what's your local rank on this host, and then you assign that GPU to this rank. Then you create your network, CUDA, create your optimizer, and the only thing you have to do here is that you have to wrap your optimizer with, you have to increase your learning rate by Horovod size. What does that mean? If you think about it, you have a learning rate that's designed to work with the number of batches, batch size that you have, right? Now you are adding, like you're 4 times increasing your batch size because you're having 4 times the workers that you had. So what does that mean? At every step, whatever gradients you're learning, you have to give 4 times more weight to them when you're applying that to your network. So that's why in Horovod, we always recommend to increase your learning rate by the size of the basically workers that you have. So after doing that, just the same optimizer instance that you created, you pass it to this Horovod distributed optimizer. So it's just wrap it with our optimizer. And then you use this optimizer just like a normal optimizer that you would use in regular training. And then finally, before starting your training, you broadcast your parameters from your worker 0 to the rest of the workers. Why do you need to do that? We'll talk about this later, but essentially because all these workers should start from the same initial set of weights. So they keep going when you apply the same gradient updates to them, they go to the same final model, right? If you start from different points, you will end up at different points. So we're gonna talk about some of these steps a little bit more in details. So now you wrote that code, so that's the script that you have, and you want to actually execute this on your cluster, right? What do you have to do? First, you have to make sure that example.py, that script, is present on all your hosts. So it's up to you how you want to put it on all these hosts, right? You can just simply as SSHing it and check out from your GitHub repository to having a shared folder and putting it, synchronizing it, right? That's up to you. Second, these hosts need to be able to SSH into one another. So if you have those two, then all you have to do is just call Horovod run, specify how many processes you have, and then the IP address of the hosts that you want to run, and how many processes are going to run on each one of those hosts. So that's how you start your training process. And then what happens is the training is gonna happen all these workers, and you can finally download your model from any of these workers because they're gonna have identical models at the end of it. So you can checkpoint locally, or you can checkpoint on the workers to some sort of a remote location like S3 bucket or HDFS or wherever you like, right? So now let's look at some of those steps that we added in the code in more details and why did we need to add those. So adjusting learning rate, I already kind of talked about this because you have more workers, so every step is worth more than a single, basically GPU training case. We also recommend to do smooth warm-up for the first K epochs. There's a Facebook paper that you can and read about this, but this is basically a very simple step you have to perform. The second step, I talked about this as well. Before starting your training, you have to broadcast your parameters to all the workers. So usually you start from root rank 0. So by contract, we choose rank 0 to be the leader, but it doesn't mean anything, it's just by contract. And then rank 0 broadcast its version of parameters randomizedly assigned at the beginning of training to everyone else. So if they start from different points with even same gradients, they're going to end up at different points. That's why we want to start with the same set of parameters. So let's talk a little bit also about data, right? This is kind of a pain point that we have seen many of our users on GitHub experience sometimes. Actually, I'm going to start from here. One thing to keep in mind, Horovod does not handle data access. So if you saw my code earlier I showed, there was nothing about how you read the data. That's up to the user. We have a recommended package that's also an open source package by Uber, Pedastorm. And then using Parquet records that we have examples on Horovod. You can look at those examples in our GitHub repository. But basically, it's up to you. You want to download all your data locally and then train. You want to stream from your HDFS, or you want to stream from your S3, use TensorFlow or PyTorch's dataset classes. It's up to you how you want to do that. But now I'm going to go back. There's the two things you have to keep in mind, or two techniques, sort of. One is that some people partition their entire data set to their workers. That means they assign a fixed set of data at the beginning of every epoch that these records are gonna be sent to worker 0, and then these other ones are gonna be used by worker 2. And that way you make sure that every record is going to be at least read once and used in the training. The other technique is sort of random sampling. So you have all your data set, and then every worker randomly samples at every training time, at every batch. And then when the epoch is done, and the way you implement this shuffling is you shuffle the data set first, you do your training in just reading by order, and then at the end of the epoch, you reshuffle again to make sure that you're not feeding the same identical data set in the same order. But again, there is not really in practice much difference between these two techniques. So it's sort of whichever you're easier and more comfortable with. Now, the currently recommended version that we have on Horovod and we use in our examples is a package that a package called Petastorm. So Petastorm takes care of sharding, shuffling, and it does a lot of IO optimization. So it simplifies a lot of the pain points and also improves performance. The way it works is that it reads from Parquet files. So if you're not familiar with Parquet files are broken into row groups. So your entire data is broken to the smallest units that you can read sequentially is a row group. They're in size of few hundred megabytes, 250, 300 megabytes usually. And they're stored in your, they're compatible with like a native data type in Spark or so on. So the way Petastorm works is that the sharding, the way it works is that it randomly assigns a subset of those row groups to each worker. So instead of shuffling the actual data, it only shuffles the list of who is in charge of which row group. And then at reading time, basically, it shuffles that list and each worker grabs their own or streams in their own row groups from the store. And this streaming is also handled by Petastorm. It's multi-threaded and it does stuff like prefetching and so on. So that kind of ensures that your training is not bottlenecked by I/O. So it helps you to improve the performance. Again, you can find examples of how we use Petastorm with Horovod to get better optimization, to get better performance with your training. Okay, now I've talked about Horovod. So you kind of have an idea of why Horovod is useful, what do you do with it, and how it helps you with doing distributed deep learning, right? There's actually more. So this is something that we've worked on for the past few months, and now it's available in Horovod. The newest release, 0.19 that we had in December has this. It's Horovod Deep Learning Estimators. This is actually something that we're very excited about it in Uber. So the idea is the machine learning that like we do, right, is more than just training one deep learning model. You start from preparing your data, then you do your model training, then you have to evaluate these models. Probably you're gonna iterate back and forth between step 2 and 3 so many times. And then you have to deploy this model, and then you're not done. You have to go back and retrain this periodically, do incremental training, so on and so forth, right? So far, Horovod that we talked about only was handling step 2, right? But how can we make this much smoother? Like how can we also make Horovod to basically be more compatible with the steps 1, 3, and 4? And basically, we can zoom out further. The complexity is more than just one model, right? It's basically multiple models that you have to handle, multiple workflows that you have to take care of. So with that, what do we need to actually achieve these goals? We need to be able to like quickly do feature engineering and prepare our data, right? Like because I mean, I talked about Horovod, but I kind of assume that magically you have your data prepared. That is not the case all the time, right? You have to, somebody has to do that work. Then you have to be able to do distributed training. That's what Horovod comes into play. You have to then to be able to quickly do evaluation. So you have a lot of records, you have your model. How do you in parallel launch jobs that are fault tolerant and do all of this? And then you have to do prediction. So you have to do batch prediction, like finally use this model for whatever you want, or do online serving, right? Spark is actually a really damn good candidate for this. It does a lot of these steps. It's been used. It's like a standard tool in the tool set of all the ML engineers, but it just, nobody really used it for deep learning so far, right? So this is what Horovod deep learning Spark estimators come into play. So basically, the idea is that we can directly train deep learning models on Horovod Spark data frames. So instead of having to do all the crazy data handling and like separately prepare data yourself, like decide how you're gonna feed that data into your model, just use the Spark. And much more simpler user experience for all end-to-end process. And also like some nice out-of-the-box features that like serializing your entire pipeline. So you can just reproduce this whole experiment later on. And not have to worry about the version incompatibilities or like some component falling apart, right? So I'm going to talk a little bit more about Horovod deep learning estimators and just show the interface and like the use case for that. So when you do Spark, when you do Spark for ETL, like it's very common. You have an extract step. You got to read your data from some store. Then you do your transformation of data, choose a bunch of columns that you're going to use, a subset of the features, do maybe some joins. And then like you usually save this data to somewhere, right? So this is something that standard people have used Spark forever, right? But the Spark also has more than that. Spark ML pipeline is part of Spark, is an open source basically component. It is actually really useful if you're doing like non-deep, it was up to now, non-deep learning models. It has these three concepts that I'm going to introduce first. So estimators, transformers, and then ML pipeline. So basically the first concept is the estimator. So a Spark estimator is like, you can think of it like a model, right? It has some parameters that it has to learn from data. So when you take an estimator and you fit it on a data frame, and data frame is your data, you get a transformer. So a transformer is sort of an immutable, like you've already trained this model and it has fixed components. Then you can take that transformer and apply that to your data and transform that data. For example, you can do prediction, right? So that's what a transformer does. And then finally, you can put a bunch of these transformers back to back, maybe ending by an estimator or just a transformer, and build a pipeline. So these transformers, I said they could be a model prediction, but they also could be your feature extractors. They could be a one-hot encoder. They could be a normalizer. They could be a vector assembler, right? All of these things could be, and actually Spark has already, Spark already has a bunch, Spark ML pipelines already have a lot of standard transformers that are very useful for feature engineering. So once you put your pipeline together, you can fit an entire pipeline. So now you're basically saying, first do these transformations on my data, then fit this model on top of it. And then finally, when you call the transform with the whole pipeline, it applies all these data transformations and then feeds the transformed data into your model, right? So you're defining everything sort of together. And this is really great, and I think very useful to basically bring software engineering principles to machine learning. So an example of this basically is like you can define a pipeline and you can have multiple multiple transformers. So an int to float encoder or a string indexer, one hot encoder. And then like you can apply all of this to your data. Sometimes you might need to fit the fit basically the transformers before actually using it. And the reason is that some transformations are dependent on the data, right? If you want to do normalization, for instance, you might need to calculate the average first. So you do a fitting step and then you do the normalization. So Spark ML pipeline has like a long list of out of the box, basically these transformers as well that are very useful, not only for non-deep learning models, but also super useful for deep learning models, right? And why not we use and take advantage of them? So now you've done your data preparation and you have your features ready to be fed into your deep learning model, right? Which Spark was really good at it. You define your deep learning model. In this case, it's a Keras model, right? Very simple, just a single layer. And then you define your optimizer with normal learning rate that you will have and all the other parameters that you would have had, right? If using old traditional Horovod way, you would have had to find a way to put that data in and like feed that into your workers, and basically from your workers read somehow, extract the model back, and then launch training, evaluation somehow again, parallelize that, right? But now we have deep learning estimators. So this is, as I said, a new release in Horovod. In this case, we have basically right now Keras and PyTorch estimators. So all you really have to do is you feed in your model, optimizer, what loss function you want to use, what metrics you want to use. This can be custom functions if you want to build. What are your feature columns? Sorry, it's a typo. In this case, like distance and temperature. Which one is your label column? Which one is your validation column? What batch size? How many epochs? And so on, right? And you basically instantiate your estimator. So I did not have to do any data handling, if you notice, right? I did not have to define how to read the data, or I did not have to adjust learning rate. I did not have to really write any Horovod code except Keras estimator, right? And I have my estimator. Next step, you can just basically call estimator.fit on your trained data frame, which is a Spark data frame. So this will launch under the hood. We'll talk about this a little bit later. Basically, the executors that will do your distributed training, train your model on your entire data set with the parameters that you basically specified, and return a Keras transformer function, right? So this step is going to take a while. After the training is finished, you have your Keras transformer. You want to do evaluation. You want to see how does this model perform. You take that transformer and apply it to your test data frame. So again, you can take advantage of all the nice things that Spark has, right? You can use as many executors as you want. You can use all the fault tolerance, all the data handling. You don't really have to worry about data again. So you can run your evaluations. And then finally, you want to save these models, right? Like you want to save them, and later on a different instance, you want to load and do something useful. So out of the box features that a Spark ML pipeline has. So you can write the whole pipeline, save it to basically wherever you want to. And then later on, you can load that and then do more transformation with your loaded basically transformer. So just notice that this transformer already contains your PyTorch or Keras models. So you can also extract the model itself if you want to. But as long as you're only working with the Spark, like within the Spark framework, you don't really have to touch the model directly. It also provides the incremental training, right? So you can basically, from your transformer, get your model and get your optimizer, and then you can instantiate a new estimator. So this estimator basically is loaded with your currently trained weights and optimizer state. And you have new data. You can throw new data and retrain, like incrementally train that model just from the point you left since last training, right? So that's the end of it. So, and just do this every day. So you basically get out-of-the-box support for all of these nice features that are, I think, great. See, time, I have 10 more minutes. So a little bit briefly, what is under the hood? So basically, you initially have your model optimizer function that you want to use and your loss function. You have your data that's on your HDFS, and you basically load that data as a Spark data frame, right? You instantiate an estimator with the parameters, and you have an estimator object. So when you call the fit function, estimator creates the Spark executors. The first step of the fitting is actually to read the data and prepare it to be consumed by the Horovod deep learning model. So these workers do a bunch of magic and then write the intermediate sort of the prepared data into temporary Parquet files on a store that you provide. The second step of training is the Horovod workers that are launched. They read that data with Petastorm. They do all the learning rate adjustments. They do all the internal, basically, Horovod magic that needs to be done. And then they train the model. So finally, the trained model, the bytes of the Keras or PyTorch model that is trained, is returned, and then it's encapsulated into your transformer object. And now your transformer object is like a object that has your trained model, and then you can pass the test data frame to it, and you can do a prediction with that. So what happens if you want to use it? Then again, workers are launched in a Spark, so you get all the parallelism and everything. You can scale as much as the number of executors that you have. These workers read the data from your original data, and then the output of this, it can be another Spark data frame that you can use in your pipeline for however you want, right? So this is, again, very high level without going too much into the details of how this works. And the nice thing is that Spark 3 will also have support for resource-aware scheduling, which means that you can specify when you're designing this pipeline that I want this step to execute on hosts that have GPUs. So you can just take advantage of GPU training in a Spark environment. So these are really good features that we're very happy that are available. So some success stories about Horovod. Horovod is used, it has a very, very active community. So it's been used in NVIDIA, Amazon, Alibaba, Oak Ridge National Laboratory, and many others that we learned about some. And it's also right now available for using today in AWS, GCP, Microsoft Azure, and Databricks. Like last year, Oak Ridge National Lab basically used Horovod on their supercomputers. They have a paper that's interesting to read, Exascale Deep Learning for Climate Analytics. And they were able to scale to very crazy numbers. So 4,560 Summit workers, beyond 1,024 GPUs. So like you can really, there's no limit, and you can scale as much as you want. They actually got a very impressive efficiency, so 90%, 90.7% scaling efficiency as well. And some of the things that we are going to, we are working right now on, and we want to have them released hopefully soon. The big one that we're really excited about is Elastic Horovod. So basically right now, one of the features that we don't have is that when you have your ring training, if any of the workers fail for any reason, your training fails, your entire training fails. And we don't have a automatically automatic mechanism to resume your training from the latest point that was stopped. So this is a little bit problematic in the sense if you want to use especially spot instances, right? That's very cheap on all these cloud providers. These spot instances, for those of you who don't know, are basically you can have a GPU instance that costs 10% of a actual GPU instance on AWS. with the downside that at any point, AWS or Google can tell you, I'm going to take this node away. I give you a 60-second or 30 seconds warning, and then I'm going to take this away. So you have to have a mechanism to be able to run your job, however it is, in a resilient manner that can tolerate that sort of disappearance of workers, right? We also have this internally on our schedulers that workers get preempted and so on. So with Elastic training, the idea is that the training process is able to scale up or down. So we can dynamically add more workers or remove workers from the training process. And we can continue our training without failing the job. That is something that's coming. So last summer, we added Facebook's Glue into our basic tech stack, which is an alternative to MPI, but it's more fault tolerant than MPI. It raises exceptions on instance failures. So it's like the first step that basically paves the way for us to get to Elastic Horovod. I mean, there are some challenges. So I have 5 minutes of Elastic Horovod, and that's basically maintaining the total batch size. So if you have 10 workers and you add a learning rate that you fix with 10 workers, and you have been training so far, so every step was worth 10 multiplied by your batch size, many of samples. And suddenly you're losing one worker, right? So if you just simply like don't scale or change your batch size, your updates at every step are going to be different than what they were in previous scares with different number of workers. So again, like we have to figure out how we're going to redistribute data or readjust learning rate. And these are some of the things that we are working on. And the other thing is Horovod is actually very research friendly. So that means that if you have ideas, you can easily come and try it out. We have a lot of university contributors and users as well. So one area that like there are papers on it and can be tested or are being tested with Horovod are the gradient compression. So when you have all these workers that are sharing their gradients with each other, if you want to reduce the amount of load on network, you can basically compress the gradients before sending them out, right? So the better you can compress, the higher usage of network and faster or higher performance for your training. Or quantization for basically the gradients as well. So again, if you have ideas that you want to try them out, or if you want to basically just do research, Horovod is an interesting and cool platform as well. So I think that's all I had. Thank you all for attending the talk, and happy to answer any questions you have. Yeah.
Deep learning on Spark. When you have deep learning in Spark, you're still using Python generally underneath to do the deep learning. Is there? I know like there's deep learning for J, which is there any work in actually putting everything in the job
No. So it's actually using PySpark. So everything, all the code you write is in Python. I mean, under the hood, PySpark eventually calls Java and JVM, but nothing that user has to deal with.
Oh, it's PySpark, not.
Yes, it's PySpark. Yes, it's PySpark. Yeah.
How is this distributed training affects model determinism? Are there any additional sources of non-determinism that are introduced in addition to regular GPU issues?
I mean, there can be some numerical challenges when you are taking averages. There can also be, you're saying model non-determinism, right? Yeah, I can think of only the numerical basically challenges that can come up with averaging the gradients and so on. I mean, also like, for example, net compressions can also impact that. So if we do gradient compression, and depending on how good you're compressing, that can totally change the way that the gradients can impact the final model.
We should take one last question before we move on.
Yeah, go ahead.
So great talk.
So I have a question about the R-reduce operation that you talked about. So after each node or GPU node send the waste, you have to synchronize at that step, right? So two questions about that. Have you seen any challenges with increasing the number of GPUs, or if you have a network that has a lot of waste that needs to be shared? And have you considered, so I remember in the HPC wars, what some people did is for this kind of sharing, instead of a all-to-all graph for sharing, they use some kind of topology that different parts are share basically some nodes between them. So you know that over time, you're going to have a convergence with the weights that you're going to share.
So actually we have, for example, we have hierarchical R-reduced. Like I didn't put all the details in there, but there's a lot of optimizations that happens, like in addition to just doing a simple R-reduce. So certainly, yes, if you have larger models that have larger number of parameters, then the network cost can be larger than the GPU computation time. And like that can be challenging in some cases. Then on top of that, there is also like, basically the way the smarter you are about your R-reduce process, you get better performance. Like it's always a bottleneck. So for example, recently we have this contribution from Microsoft that they added the add-a-sum operation, or like basically reduce, that does a little bit smarter than it's a form of tree reduce, but it's more smarter. And that actually can increase the performance time by 10 to 20%. So the answer to your question is yes, we have seen challenges, but also we have solutions for more complicated cases that require a little bit more customization. I think out of time, so thank you so much, and yeah, let's listen to the next talk.
Thank you, Fardin.